In section 8.3, we're going to be looking at equations of lines. So the lines that we're looking at are linear equations, perfectly straight lines. And so we're going to be looking at equations that involve an x and our y variable. And linear equations are one of the most common relationships that we see used out there in the world. And so we want to be very comfortable with writing these algebraic linear equations as well as graphing them and just being used to manipulating them in the different formats that we'll see. So by the end of today's section, you want to be able to know how to write the algebraic equation of these linear equations in the various formats. The two common ones are the point slope and slope intercept form that we'll see in a second. And then also knowing how to take that algebraic equation and graph my line. And then we'll end looking at how to generate our equation when we're given particular information, in the case of looking at parallel and perpendicular lines that are given. So there's three formats that a linear equation is potentially written in. First is the point slope form. Then we could have the slope intercept form. And then there's also the standard form. So kind of look for those particular names as you're solving through the problems in the homework. They may request you to have your line be given in one of these particular forms. So the point slope form, that's the equation that we see here. Y minus y1 equals m times the quantity x minus x1. And this particular format we want to use for our lines if we're given information regarding a point on the line and then the slope of our line. So it's pretty much in the name. Point slope form you would use when you're given a point and a slope. Now if I look at my equation, we have a y. We also have this little y with a 1, what we call a subscript of 1 on it. I also have a normal x and then x with a subscript of 1. And there is a difference between those two, even though they both have x and both have y. The values without any subscripts, so just normal x, normal y, those are your actual variables x and y. So those are going to stay in my equation. The values that would get replaced are the m, and m is always the default placeholder for our slope. So m would be replaced with some number representing my slope. And then the x with a subscript of 1 and y with a subscript of 1, those are also going to be numerical values that get replaced. Those are the x coordinate and y coordinate for that given point that we've been told. And part of the reason why we use that subscript in our equation format is we still want to represent that it's the x value and y value of my point, but it's not playing the same role that the variable x and y is in the equation. So that's why we see that little subscript notation to notice that it is relating back to the x value and y value for the point, but it's not going to be playing the role of x and y as a variable in our equation. So if we plugged in those three values, we would get an equation that has y and x being related with numbers being subtracted or multiplied. The second equation format is the slope-intercept form, and this is likely one that you've seen before, the y equals mx plus b equation format. And again, the use for it, when we would likely use that form, is when we're given the slope for our equation and the y-intercept. So when they say intercept, they're referring particularly to the y-intercept. And so similar to our previous equation, y and x would be our variables, m would be some numerical slope value that gets replaced, and then b is the y-coordinate for the y-intercept. So we don't have an x and a y-coordinate like in our point slope form, because the x-coordinate, if you're talking about a y-intercept, the x value is always 0. So really the only place in my point where the y-intercept is going to be changing value is the y value, what we call this b. So whatever your y value is for the point that is your y-intercept, that's going to play the role of b. And then the standard form that we see here, it has capital A times x plus capital B times y equals c. The capital A, B, and c are just placeholders. Those are going to be numbers that are given to us. So it could be something like 3x minus 2y equals 7. right? So the key difference there is that unlike our previous equations where only y was on the left side of my equation, the standard form in particular has both x and y on one side of the equation, and then what we call our constant term, right, the non-variable term, on the other side of our equation. And in terms of value, right, for the standard form, it doesn't really give us much information. Our other two formats, we can kind of look at the location of our values and figure things out, like the slope, right, is going to be your multiplier to x. In point slope form, I know whatever number I'm adding at the end is going to be my y-intercept value. When I see the subtraction on each side of the point slope form, we know that's the x and y value of my point. We don't have that same sort of meaning implied in the standard form. So this 3, the -2 and the 7 that I gave in my example, they don't really have any meaning for us. So the standard form is not as often used because it does lack those key meanings, but there are other places where it's beneficial to write our equation in that particular format. So kind of be aware that it's out there, and you may be requested to write your equations in that same standard form. If you are asked to put it in the standard form, just keep in mind that x and y have to be on the same side of the equation, the constant on the other side, and then a general rule of thumb is we want these coefficient values, the capital A, B, and C, we don't want those to be decimal or fractional numbers. So you may have to multiply both sides of your equation to get your coefficients to not be fractional or decimal values. The last two equations I have listed here for vertical and horizontal lines, those are more special cases because they don't involve both variables, right? We're only seeing x or just y. So our vertical line, that's our line that runs perfectly straight up and down. Our horizontal line is the one that runs perfectly straight from left to right. And because they don't quite act like our other linear equations with like a slant to them, they're not going to involve both variables. They're only going to involve a single variable. So anytime I see an equation that just has x equals some numerical value, so for example I could say like x equals 3, that is a vertical line. The fact that I only see an x value and then a numerical value. There's no y involved. And similarly, if I just see a y equals some numerical value, like y equals 2, that's going to be a horizontal line. So just be aware of those two special cases as they can pop up as you solve through problems. So in our first example, we're going to find the standard form of an equation of a line with a slope of 1/3 and passing through the point -3, 2. So we have some key information here that we want to work with. The first thing is they are telling us how they want the answer formatted, that they want it written in the standard form. So the standard form, that's the ax plus by equals c. So that's the format where both x and y are on one side of the equation, the constants on the other side, and we got to find these capital A, B, and C values. They also told us some information about our line, that the slope is 1/3. That's our m value. So slope is 1/3. And also the location of the point on my line, that the point is at -3, 2. So although we want our answer written in the standard form, it's not really the best format to figure out the capital A, B, and C value given the slope and the point like we have right here. So the best place to start is to generate your equation based off of the information you've been given. I've been given my slope and I've been given a point on my line. So no big surprise, the equation to go to is the point slope form. So the point slope form is going to be the easiest way to generate our equation given those two bits of information that we have, the point and the slope. And so the first step, anytime you're using one of these formats, to make it easy for us to fill in numbers and also easy for our reader to know what steps we're going through when we're solving, is to write down the blank equation. So I'm just writing the generic point slope form, nothing has been replaced. It's the exact same form that we saw on the last page. Now once I've written that down, now we can go ahead and start replacing some values. So I know my slope is 1/3. So I'm going to go ahead and replace my 1/3 value. The x and the y that we see in our form without any subscript of 1, those are the variables, so those are going to stay. And then we also want to fill in the point that was given to us. So the point, the x location is that x1 that we see in our format, and the y location is the y1 that we see. So x1 is a -3, and this is the one place we want to be really careful using the point slope form, is that we have subtraction in the format, and you could get double negatives like we're seeing here. So there's the negative that came from my equation, but then there's also the negative that was associated with my 3. So there could be that double negative that we gotta keep an eye out for. And then on the other side, since y1 was 2, there we don't have to worry about the double negative. So all that I've done is I replaced m with 1/3. The x1 was our x value for my point, which was -3. The y1 was the y value for my point, which was 2. And then we want to take this and go ahead and simplify it down. We're trying to make it look like the standard form, right, with x and y on one side of the equation, the constant on the other. So to start that off, we'll go ahead and simplify this down. So one thing I can do is fix that double negative situation. So x minus -3 is x plus 3. And then I have this 1/3 that's multiplying to the quantity x plus 3. We definitely want to clean that up as well by distributing. So I'm going to go ahead and distribute my 1/3. So 1/3 times x is 1/3 x. 1/3 times 3 is going to yield a 1, right? 3 times 1/3, 3/3 is 1. And then I'm just going to carry down any operations that we didn't change anything to. So the y minus 2 will carry down. So this definitely doesn't look like the standard form. We want to get it to look like that standard form. So one key step is going to be moving my x and my y variables to be located on the same side. So here we have it located on the left side of the equation. I can just do the same thing for mine. The y is already on the left, but the x isn't. So I'm going to go ahead and subtract my 1/3 x to move it over to the left-hand side. So this would be -1/3 x plus y minus 2 equals 1. So now x and y are both on the left side, but I'm not supposed to have that value of 2 there. So I can similarly do the inverse operation. Instead of subtracting, we can add the 2 to move it over. Now I have a value of 3 on the right-hand side. So this almost looks like the standard form. The only issue with it is it doesn't fit what the standard form needs in terms of the coefficient numbers, those capital A, B's, and C's. And that's because of our fraction, that -1/3. So the standard form does not allow for decimal or fractional values for any of its coefficients, so we have to fix that, right? I have to fix this 1/3 that we're seeing. And we can fix it. The trick is to use the same tricks we have been using for algebra to get rid of fractions, and that's to multiply your denominator, right? So I'm going to fix the 1/3 by multiplying by our denominator, right, the 3. So multiply by 3. So I'm going to take my equation and we'll do 3 times that value. So here I'm just writing down the equation again, and we'll show we're going to multiply both sides, and we do have to multiply both sides because that's how you keep equation balanced, right? Whatever you do to the left, you got to do the same thing to the right. So I can't just multiply the left side. We got to balance our equation by multiplying the right side. So on the right side, 3 times 3 is going to get me a value of 9. The value of 3 that we're multiplying on the left side needs to distribute through. So 1/3 times 3 is going to cancel out our denominator, leaving a -1x. And then 1y times 3 becomes 3y. So that's our standard form. I have my x and my y located on the left side of the equation. Constant is on my right-hand side. All of our coefficients for our variables are not fractions or decimals. Example 2, we want to find the point-slope form of an equation of a line passing through the points 2, 1 and -1, 3. So again, here they're telling me a bunch of different things. They're telling us information about our line, that it goes through those two particular points, and it's also saying the format it wants the answer to be in. It wants it to be in the point-slope form. So the point-slope form was the one that we just used a little while ago. Y minus y1 equals the slope m times x minus x1. So that's going to be the format for our answer this time. And they did tell me our 2 points. So I'm going to go through the point 2, 1 and -1, 3. Now here, for the point-slope form, even though we do have some information regarding points, we are missing the slope. I need the slope in order to complete this point-slope form. So here we actually kind of have an initial step that we have to go through. We first have to find the slope. And we've talked about slope in the past. There's lots of different ways to think about slope. It's rise over run, or the change in your y divided by change in x. In this instance, because we're given 2 points, probably the best format that we learned for slope that's going to be helpful here is the slope equation that we've seen. So this is our slope equation. It's y2 minus y1 divided by x2 minus x1. And again, the y's and the x's that we're seeing, they do have subscripts, so they're referring to points here, the 2 points that we were given. And the subscript of 1 is just referring to some first point, and the subscript of 2 to some second point. And there's no particular ordering here. It doesn't matter which one we think of as the first point or second point. The key thing is that whatever I decide a point to be, like this, if this 2, 1 is my first point, right, this is my x1, then the y coordinate goes with that, right? So if I make that judgment call, 2, 1 is considered my first point, those will both be the same x and y subscripts, and then the other point would be the other subscript. So if you had chosen differently, if you had wanted -1, 3 to be the x1, y1, that's fine. What we'll see is when we perform this slope equation and plug in our values, you're going to get the same fraction in the end, regardless of the labeling that we chose for our points. So I'm going to take my equation and go ahead and replace our values. So y2 I had selected as 3, y1 was 1, x2 was -1, and x1 was 2. And to simplify this, we need to go ahead and perform the subtraction on the top and the bottom of our fraction. So 3 take away 1 on the top leaves me with a 2. -1 minus 2 on the bottom leaves me with a -3. So our overall slope is -2/3. Here, we're seeing the negative in the bottom, but that doesn't really matter. I can pull the negative out in front or let the negative hang up top with the 2. The idea is that the overall value of our fraction is negative. That we'd have technically one part of our fraction, either the numerator or denominator, being positive, and the other one would be negative. So now that I have my slope, we can go ahead and use that point-slope equation. So that's going to be where we can start. So I'm going to write down my generic equation without anything getting plugged in. And then I'm going to go ahead and plug in my values. So I know my slope we just found, that's -2/3. The x is our variable and y is our variable, so those don't change. And then the x1, y1 is relating back to a point on my line. But here they gave me 2 points on my line. We have the 2, 1 and the -1, 3. So it doesn't matter which one you choose to be your x1, y1 in replacing it in the slope form, point slope form. What would ultimately happen, even though they look a little bit different, once you simplify your equation down to the y equals mx plus b form, they'd end up being exactly the same. So here we kind of have two different ways that our answer could look depending upon the points that you pick. So say I picked the 2, 1 point, my x1 would be a 2, my y1 would be that 1. Alternatively, right, we could have picked it the other way, and so it does look like it makes a difference when it's in this point slope format, but I can assure you it really doesn't, right? That we're really just talking about the same line again. So the other format would be a -1 for the x1 and a 3 for the y1. And maybe the only thing we'd want to do to reduce this down would be to fix that double negative issue that we're seeing. So this would be y minus 3 equals -2/3 x plus 1. So they wanted our answer in the point slope form, so we would end there. Either of these two answers would be counted as correct. They're both describing the same line, believe it or not. And they do look like they're different, but they really aren't. Once you simplify it down, you're still describing the same line. The only difference is we're using at 2 different points on the line when we're generating this point slope form. In our next example, we want to graph algebraic equations. And so you can see that there's 2 different formats here, because you could be given your equation in any of our formats. So the first equation we see, I have y equals 3/2 x minus 2. We would compare that to the 3 forms that we have, the point slope form, the standard form, and the slope intercept form. And hopefully you guys can see this definitely fits best the slope intercept form. It doesn't look like point slope because we don't see those values being subtracted or things in parentheses, like the x minus a value. It also doesn't look like standard form because we don't have both variables on the same side. So here the fact that we have y isolated, that's a big tip-off that this is our point slope form. And since it's the point slope form, we can really easily identify our slope and our y-intercept. So the slope is going to be the number that we have multiplying by x, what we call the coefficient of x. So here our slope is 3/2. And then the y-intercept, that's the number at the end that we're adding or subtracting. So here my b value is -2. And then just remember that b quantity is representing the y value of our y-intercept. So that's talking about the point 0, -2. And that's actually enough information for us to be able to graph our line. And we'll see how we do that in a second. Now before I start graphing this though, we do have an issue with our graph, and that is it doesn't have a scale listed. And while it's very common to allow each tick mark to count by 1, that's not a default. That we have to state what we want the x values to count by and the y values to count by. So if you are given a blank graph like this, that's the very first thing that we should do is go ahead and label it. And for our purposes, I don't think we need to pick a bigger scale than every tick mark being a 1, and so I'm going to keep that. So you could go through and label each and every tick mark 1, 2, 3, 4, 5, and so on. But what usually tends to happen is our graph can get pretty crowded with numbers. So an alternative to that is to skip a couple tick marks. So every 2 tick marks or 3 tick marks, you can skip and just label those. So I'm just going to label every other tick mark. Those will be my evens. So 2, 4, 6, and 8. And we want to do the negative direction as well. So -2, -4, -6, and -8. And then we want to do the same thing for our y's. And why we want to label both directions on the x and the y-axis is because the scale doesn't have to be the same. I can count 1, every tick mark has a value of 1 on the x-axis and choose a completely different scale for the y-axis. So we want to make sure we label both so that there's no confusion. And again here I don't foresee us running into very large y values that we would need a bigger scale. So I'm going to go ahead and label it the same way. Every tick mark counts as a value of 1. And to kind of keep it less cluttered, I'm just going to label every other tick mark. And we want to do that going in all 4 directions. So this is a step that a lot of students skip, and that's a bad thing, that if you don't label your graph, whoever's reading it doesn't have any idea of where the points actually lie. So it's a very subtle but important thing to label your graph. So now that I have it labeled, I can go ahead and start graphing. So the first thing we need to graph is our point location. We always start with the y-intercepts, and once we have that point on the graph, then we can use our slope to generate more points. So I'm going to graph the point 0, -2, and then our slope is telling us how to get to another point on our line. So one of the ways we interpret slope is rise over run, and rise is referring to our movement up or down on our graph. So here this is a +3, so that would mean I'm moving up 3 units. And then your run is movement left or right. And again, we see a positive value there, and the positive direction on the x-axis is to the right. So that's telling me essentially the directions how to get to the next point. I'm going to go up 3 units, or 3 tick marks, and then to the right 2. And that would be the next location of my point. And I can keep doing that for as many points as I want on my graph. So 1, 2, 3 up, to the right, 1, 2, 3 up, to the right. And depending upon your drawing skills, your graphing skills, if you are pretty good at drawing straight lines, then you may need fewer points, right? You could get by with maybe just 2 or 3 points. I find for myself, unless I have a nice ruler on hand, that drawing accurately straight lines is a big challenge for me. So I choose to have as many points as possible in my graph to have a better hope of making it a perfectly straight line. So that helps me generate points kind of up to the right-hand side, but I want more points. So what we can do is reverse the direction. So literally doing the opposite of what our previous direction was. So instead of going up 3, I could go down 3, and instead of going to the right, we go left 2. And what we'll see is our trend of our line is still following the same direction. We just reversed it to go to kind of the other part of our graph. So there I have plenty of points. We can go ahead and graph a nice straight line here. Oops. And if you're doing this by hand, a good tip would be go ahead and use a ruler or something that can serve as a straight edge, even if it's the side of your notebook. We want to get nice straight lines. And then the other important thing that we need are arrows at the end of our line. And that's important because our lines are going to keep on going, even in the sections on our graph that we don't see. And we want that to be shown. So those little double-headed arrows indicate that your line keeps going. If you forget and you leave off those arrows, what you're really implying is that you have what we call a line segment, right? It ends at those 2 end locations. It doesn't keep going like it actually is. So there's our first line. And now I want to go ahead and graph the second line, this part B. This time around, though, it's not in the slope-intercept form. We can see it's actually written in the standard form. And I could get it into y = mx plus b. So here we kind of have 2 options. So option 1 is I can get it into slope-intercept form by solving for y. And then essentially what I would have is kind of like what we saw in part A. We'd be given a point, like our y-intercept, and then we'd be able to calculate the slope. So you can do that. I want to show you guys, though, kind of the one strength of the standard form, and that's that it tells you your x and y-intercept values very, very nicely. So I'm going to model that here for you guys. So if I didn't want to change it into that slope-intercept form, then we can use the intercepts. So that would be what we call kind of option 2. So option 2 is to use the intercepts. So if I'm going to use my intercepts, we need to go ahead and calculate those values. So the x-intercept, that occurs when y is 0. So we're going to have some unknown x value that we need to find, but the y value is going to definitely be 0. So I can go ahead and take our equation, the 3x plus 4y equals 12, but I'm going to replace the y value with a 0. And when we do that, some nice math happens for us. Anytime you can multiply by 0, things tend to get nice and simple. So here, the 3x would stick around. However, 4 times 0 is 0, and I don't actually have to show addition by 0 because that doesn't change the 3x there when we add it. So I really am just left with 3x equals 12. It's almost like that 4y kind of disappeared on us. And then I could solve it. So I could divide both sides by 3, and I get that x is 12 divided by 3, or 4. So that's going to be 1 point on my line. So that's our x-intercept. It's 4, 0. And we can see that actually didn't take much effort, right? Once I knew to replace y with 0, the solving process happened really quickly. That could be even something, depending upon your comfort level, you could even do that in your head, right? It wasn't a very difficult calculation. The y-intercept is pretty similar. The only change compared to what we saw is that now the x value is 0 and the y value is some unknown point that we're solving for. So we're still going to start with the same equation, but this time x gets to take on the value of 0. And very, very similar to what we saw in the last one, because x is 0, it's almost as if that 3x term goes away. 3 times 0 is 0. Since we're adding it to 4y, I don't actually have to show the addition by 0. And then we just solve for our y variable. So I could divide both sides by 4, and y is 12 divided by 4, or 3. So that's the second point. Our x-intercept, or pardon me, y-intercept is 0, 3. And why that's helpful is because a linear equation really only needs 2 points. Once you have 2 points, you can go ahead and draw a straight line with it. And those are 2 very nice points that we can use to graph. So I'm just going to go ahead and plot those 2 points on my graph, and then just connect them with a nice straight line. So our x-intercept was 4, 0. So when x is 4, y is 0, that'll be 1 point. And the y-intercept was 0, 3. So when x is 0, y is 3. And then once I have those 2 points, we can go ahead and probably use a ruler or something, a nice straight edge, to draw our straight line. And there it is. So there are our 2 lines. And again, just remember, once you draw your straight line, make sure you show the arrows on each end, that your line's going to continue on forever. Example 4, we want to find the slope-intercept form of an equation for a line that's perpendicular to the graph of 2x plus 3y equals 6, passing through the point -4, 5. So here we have a lot of information we want to pay attention to. So they want the answer in slope-intercept form, or y equals mx plus b. So we know we want to get our answer into that format at the end. And they're very specific on the type of equation they want. They want it to be perpendicular to the line that is given, but they also want it to pass through this point -4, 5. So the thing that's tricky about these type of problems that I like to call the parallel and perpendicular problems, right? You're going to see that parallel to or perpendicular to wording in there, is that these are really kind of like 2-part problems. So part 1 really is finding the slope. And what I mean by that is they gave me an equation, this 2x plus 3y equals 6, and they told me they want our line to be perpendicular. But that doesn't tell me offhand the slope of our line. We got to do some work to find it. So that's going to be the first part, is finding the slope. And then once we have the slope, we can go ahead and continue on to part 2. And then part 2 is to use the slope and the given point to generate our line. So we'll start with part 1 to start. So we were given the equation 2x plus 3y equals 6, and we can hopefully start recognizing that's what we recognize as our standard form. And this is not a good format to identify or know what the slope is. So the first thing we want to do is we want to find the slope. Of this line. And the best way to do that is to change its format. We want the best format to find slope, to recognize slope, and that's y equals mx plus b. So we don't want the standard form, we want the slope-intercept or y equals mx plus b form. And the good news is we can easily change our equation into y equals mx plus b. The trick is to solve for y. So I'm going to subtract 2x to move it to the right side. I'm left with 3y equals negative 2x plus 6. I almost have my y equals form, I just need to divide them by 3. So when it's all said and done, I have y equals negative 2 divided by 3 times x, and we do want to break up our division between the x term and the constant term. So that way we can see it exactly in the mx plus b form. So that's why I wrote negative 2/3, and then 6 divided by 3, that's a positive 2. So if I compare that to y equals mx plus b, I know that my slope, m, is that number in front of x, the coefficient of x. It's negative 2/3. Now before I head off into part 2, which is generating the equation of our line, we don't really know our slope yet. All that I know is the slope of the given line. We want to be careful because we want the perpendicular slope of that line. So there's 2 key relationships we got to be aware of, parallel and perpendicular. When our lines are parallel, the slopes are exactly the same. So if this question had asked for the parallel line, then negative 2/3 would be my slope. However, they didn't ask for that. They asked for perpendicular. And the perpendicular lines also have a relationship in their slopes, and that's that the slopes are negative reciprocals. And so what does that mean? That means that my negative 2/3 really isn't my slope. I need to get its negative reciprocal. So the negative piece means we change signs. So it's currently negative. Negating a negative makes it positive, right? So we change the sign. And then reciprocal means we're going to flip our fraction. So right now it's 2 divided by 3. I'm going to flip that so the 3 is on top and 2 is on bottom. So the perpendicular slope that we need is actually 3 divided by 2. And this is the funny part of this process. We went through all of that work to really just find that single number, that the slope was 3/2. All the rest of the things that we found, the equation of the given line, its y-intercept, all that information we don't even need, right? We just needed to know the slope and get our perpendicular slope. So now that I have the slope that we actually need, our perpendicular slope, I can use that with the given point. So they want our point that our line will go through to be negative 4 or 5. So I want to generate my equation that has that slope 3/2 and goes through that point negative 4 or 5. And again, thinking of our 3 formats, which is the best one when you have a point and a slope given, that is our point slope form. So I'm going to use that point slope form to generate my equation. So just like before, we're going to leave our variable xy, and we're going to replace our slope number, the x value of our point, And again, we have double negatives we have to correct here for the x value of -4 and then the y value of 5. So when we simplify our answer down, this is y minus 5 equals 3/2 x, and then a double negative will go to +4. And I might be tempted to say that's my final answer, but if we look back at the original question, they didn't want it in point slope form, they wanted it in slope intercept form, y equals mx plus b. So I need to go ahead and get it into that form. So we're not done here, we have to go ahead and solve for y like we did previously. So I'm going to go ahead and distribute my 3/2 to start. So this would be 3/2 x plus 3/2 times 4, that's 12/2 or 6. And then I need y by itself. I can't have that 5, that minus 5 out there. So I'm going to go ahead and add the 5. And we get y equals 3/2 x, 6 plus 5 is 11. So that's the format they asked for, so that's where we have to take our final answer. In example 5, we're going to go ahead and do some applications of our linear equations. So again, linear equations happen all over the place, and they still follow the same rules. We're going to see slopes, we're going to be given information that represent points, and we want to build our algebraic equations and potentially graph them. So in example 5, it says in 2015 the revenue for Starbucks was $19.6 billion, and it increased at a rate of $1.7 billion per year. And we want to write a linear equation of the line in slope-intercept form that models this information. And they gave us some help. Anytime you're dealing with years, it's really tricky to capture and represent any variable that's representing a year. So it's very typical to go ahead and have some generic year represent a year 0. So they want us to treat 2015 as year 0 in our model. So we want the slope-intercept form, y equals mx plus b. And so to generate that equation, we need to know m and b, or we need to figure out those values. So they did tell us in 2015, which is our year 0, so 2015 represents year 0 for us, that the revenue was 19.6 billion, or 19.16 billion. And if you notice, they didn't put all those extra zeros to represent the billion, because that's just going to make our math so much harder with all those extra zeros. So it's really common when the numbers get large like this, where you just have a decimal representation and then you remember that your units are in billions, right? So I'm just going to remember that this is in billions. So that first part of our sentence is actually describing a point for us. When the time is 2015 or year 0, the output, our revenue, is that $19.16 billion. And then they also told us that our value increased at a rate of 1.7 billion per year. And anytime you see that keyword rate, or you have something given, an amount per something, that's a huge hint that you have the slope being given to you. So our slope is that $1.7 billion per year. So actually, I was very fortunate in this example. I know my slope, that's the 1.7 value. And then if you look very carefully at the point that was given, because x is 0, this is your y-intercept point, right? Your y-intercept point is the only point that has x with a value of 0. So that means that my b is that the 19.16. So here we don't have actually much calculation to do at all. We're just going to take mx plus b, our slope-intercept form, and replace m with our slope number, which was 1.7, and b, which was the y-intercept number of 19.16. And that's your equation. One thing that we may want to include kind of as a footnote or at the end here is that y is dollars in billions. And that's helpful just because we did essentially what we call scaling. I scaled that variable y in terms of billions of dollars. Now for part B of our question, we want to use our model that we found to predict the Starbucks revenue in the year 2025. And this is where really these linear equations are the most helpful, is once we've discovered a relationship, if we can generate an equation for it, we can then use that equation to help us predict other values. So obviously it's not the year 2025. We can't verify if this is true or not, but it lets us at least make a prediction based off of the current information that we do have. So the equation that we found on the last example, it was y equals 1.7x plus 19.16, where the y value is dollars measured in billions, and then the x value represents the years after 2015. And that's important for us because now that we're talking about the year 2025, we got to put that back in terms of our starting year. So x was 0 when it was 2015. So I need to see how many years have passed since 2015, and this is not a difficult calculation. It's 10 years that have passed. So that 2025 represents the year 10, or when x is 10. So I'm going to take my model, replace x with those 10 years that have passed, and just crunch the numbers. So we could type this in one step to our calculator or take it one piece at a time. 1.7 times 10, that's 17. Added with 19.6, that's 36.16. And we want to put this in the context of our problem, so I'm going to write this as a sentence. So Starbucks will be earning 36.16, and this is where the scaling is important. This is billions of dollars. In 2025. And before everybody goes out and invests heavily in Starbucks stocks, this is just an example problem, people. We don't really know if Starbucks is going to be that successful in the future, but you know, here's hoping, right? And example 6, we can see another linear equation application. So Kim graduated from college in 2015 and has been repaying her student loans. 1 year after graduating college, Kim owed $45,500 on her student loans. Now, 3 years after graduating college, Kim owes $37,500 on her loans. And we want to write a linear equation for our line and slope-intercept form that models the information, allowing for 2015 to be treated as year 0. So this seems very similar to what we just did, right? That we want our answer in slope-intercept or y equals mx plus b form. They gave us a year to treat as year 0. So in 2015, that's when x is going to be 0. And if you're curious why on this problem and the last problem your variable x represented time in years, that's a very common setup. So time tends to be our input variable in situations like this. Because you kind of have to know the year to then figure out what either your revenue was for Starbucks or the student loan amount that's remaining. So in that sense, you need to know the year to determine your value. So that's why x is our input. And then they gave us some information. So 1 year after graduating, she owes $45,500. So that's a coordinate for us. 1 year has passed, right, after graduating, so that's when x is 1. And then the y can represent her college loan amount. So that's the $45,500. And then 3 years after graduating, she owes the $37,500. So again, this is kind of like points, like xy coordinates. So to find my equation y equals mx plus b, we need to be able to replace m with some numerical value and b with some numerical value. And here we can see we weren't given either one. Unlike the last example, They never talked about her rate of payment or said dollars per year that she was paying, so the slope wasn't given. And between our two coordinates, we don't have x being 0. So the y-intercept point wasn't given either. They never mentioned to us what her original loan amount was when she graduated. They just gave us the snapshot of what it was 1 year after she graduated and then 3 years after she graduated. So we do have quite a bit to find here, but that's okay. The first thing that we need to find is the slope. And there's a bunch of ways that you could calculate slope when you're given two coordinates like we have here. The fastest way is going to be using our slope formula, y2 minus y1 divided by x2 minus x1. And it doesn't matter how you choose to label your points. As we mentioned previously, just go with the choice and then do your calculation off of there. So here I just happen to choose y2 to be the 37,500, making y1 the 45,500. So then x2 would be 3, x1 would be 1. So we'd find the difference. So on the top, that's a negative 8,000. And on the bottom, 3 minus 1 is 2. We can go ahead and reduce that to negative 4,000 over 1, or just negative 4,000. So that is our slope. But I still need to find the y-intercept. And there's a couple ways that we could do that. I've shown you twice now. You could use the point slope form. Y minus y1 equals your slope m times the quantity x minus x1. You can still go that route. We have the slope now, and we could use either of our 2 points. Another option I want you to be aware of, though, especially because we want our answer in y equals mx plus b form anyway, is you can use the slope-intercept form. The trick, if you do go down that route, right, so here I need to find b, that's what I'm looking for, is we're going to replace our slope number, so that was a negative 4,000, and I'm going to pick one of my 2 points, it doesn't matter which one, to serve as temporary placeholders for the x and for the y. So I'm going to let x be that x value of 1, and then y was the 45,500. And why I did that, why I replaced x and y, was so that then I have an equation with just b, and I'm able to find the b. So that's a nice tricky way that you can use the y equals mx plus b form to find your y-intercept, is you can temporarily replace one of your coordinates for the x and for the y. So negative 4,000 times 1 is negative 4,000 there. And I need to solve for b, so that means I need to add the 4,000. And so b is 49,500. And then this method, the only thing you have to be careful about is I haven't found my equation. All I found was the b. I still have to go back to y equals mx plus b and now plug in both the slope and the y-intercept. So that's the only tricky part if you do go down this route, is you have to have the forethought to go back to your equation and plug in your slope and y-intercept. So my slope was negative 4,000. The y-intercept was 49,500. And our last part is to go ahead and use that model now to predict when she's going to pay off her student loans. So the equation that we had, negative 4,000x plus 49,500, is actually telling us what's happening with Kim's loans. The negative 4,000, that's our slope. That's the rate that she's able to pay it off per year. So she's paying off $4,000 per year. The 49,500, the y-intercept or b value, that's her initial value. So she started the day she graduated with $49,500 in student loans, and she's paying it off by that 4,000 amount each year. So if we want to predict the year that she's going to pay off her student loans, the year is x, right? So we're going to be solving for x. And when she pays off her student loan, here's the tricky part. Her payoff happens when her balance, or y, is 0. So that's the tricky part here, is that there's that implied value of 0. So we want her balance to be 0. And the x will be the year that that occurs in. So all that I did was took my equation and replaced y with 0. And then we can go ahead and solve this equation. So I'm going to subtract over the 49,500. So negative 49,500 equals negative 4,000x. And then divide out the negative 4,000. So being careful there because we are dividing two negatives, the result's going to be positive. And it doesn't come out all that exactly. I believe it's 12.375. So it's over 12 years. Here, because we're dealing with a practical situation, we would kind of consider this as a round up scenario, right? It takes more than 12 years, so we kind of think of that as 13 years to fully be able to pay it off. But if you notice, they didn't ask for how many years. They said in what year. So we have to put this back in terms of when we started, right? So x was 0 in 2015. And all that 13 is describing is how many years have passed since then. So I need to add my 13 years onto that. And that would be 2028. So she would pay off her loans in the year 2028.